So up on the board, I have this example right here. It does some stuff. Quickly turn to the person next to you. What effectively does this program do? Tell the person next to you. All right, anyone? Yeah. Yeah.
It creates or writes to the file system. It is output.txt plus the message hello world.
Yeah, perfect. Okay, so when I run this, it will open up this output.txt file, and it will put inside of it hello world. So let's quickly compile this. So I can do g++ hello world -o main and /main. Okay, so we should see, yeah, nothing is outputted, but if we now look at output.txt, we can see that we have this new file that was just generated. Okay, cool. We've probably seen this before. Maybe you haven't seen this write command before, or function. Have people seen write? Okay, cool. There are other obfuscations or abstractions away. Write, it's actually really cool. Write is it's called a syscall. It's an operating system provided function. And what it does is it will open up a file, or I guess it will take a file that has already been opened, and it will write data into that file. But the idea of files is all related to operating systems. So this write function is actually provided to you by Linux. And yeah, if you can go into the documentation of Linux and you can read all about what this write function will do. Effectively, it will just takes a file, puts data into it. Okay, cool. Let me quickly just kind of mess around. Well, this fd right here, notice it's an integer. So, okay, actually, let me just play around with it. Let me just put the number 1 here. Okay. So that's kind of weird, right? I'm just hard-coding this value. Okay, quickly turn to the person next to you. What do you think is going to happen? Maybe it'll segfault, maybe it'll do something. What do you think is going to happen now? So I just changed it by putting a 1 here instead of file descriptor. All right. It's going to change. Okay, anyone know? Anyone know? Actually, okay, I'll just run it. We'll see what happens. So I'm going to run it. What happened? Printed out hello world into the command line. Okay, that's kind of weird, right? So this 1, it seems like anytime we take this file, it actually prints out to hello world. And that's because what 1 is 1 is a hard-coded value that every program starts with, every program that runs inside of Linux. This program will, every program will be given this value of 1, and every time you write to 1, it is the same effect as if instead of opening this output.txt, instead it opens this other file called dev.stdout. Has anyone seen this before? Dev.stdout. So dev.stdout is a file in Linux where anytime you write to this file, anytime a program writes to this file, now the text will be outputted to whatever console you are working with. So if I now run this, so notice I'm now going to be using the file descriptor that was created when I open up this dev.stdout. So if I now run this, then once again, you can see it prints out hello world. Even though, yeah, I'm writing to this file, right, this file descriptor, but the file itself is dev.stdout. Okay, cool. All right, that's a little hook of what's going on here. So has anyone seen this before? Okay, not many. Yeah. This is how Linux, and honestly, very similar for Windows as well, and definitely, yeah, macOS as well. This is kind of just the design decision that they made when trying to think how to implement printing out to a console. And it's kind of arbitrary. It's just they already had a file system handy. They already had files implemented. They have all these write and read and open functions that you have access to. And they just thought what if we just add on this extra like hard-coded file that is called dev stdout, and just anytime you write to it, it prints out to the console. So they kind of just took advantage of what they had access to already, didn't add any extra like weird features to the operating system. Instead, they just created a new file and said, like, this is now stdout. So it's kind of arbitrary, but that is how printing works to your computer, is it's all handled by the operating system. So like you could create your own operating system with an entirely different method for printing out to the command line. For example, like maybe you go and create your own custom video game console, okay? And maybe there is some way that you need to print out to the console. So this is how Linux does it, but the Banana Slug emulator, your emulator should do it in a slightly different way. So I'm going to walk through that really quick. So, okay, really quick. So here I have my starter file right here. How do I extract out all of the files inside of this tar.gz? Shout it out. tar-xzf. Yeah, xzf. Cool, okay, good. Make sure you know that. Okay, I mean, let me quickly make a starter, or a, yeah, that's fine. Banana, yeah, that's fine, okay. Okay, yeah, so I'll do tar-xzf. Okay, cool. So now inside of this banana directory, I have all of the files that were inside of this tar.gz, and then now I can open up the Banana Slug documentation. And if I go down to the I/O section, so we barely looked at the I/O section yesterday, but this is the I/O section, and most of it, at least this first section, is all dedicated to the controller input, which you will probably emulate with like keyboard input in your emulator. But let's skip this for now because that'll be related to checkoff 2. Instead, we will go to the debug I/O. Anyone read this part yet? Okay, cool. So debug I/O. So what this says is, so in order to access this like std in, std out, and whatnot, so we can read what it says. It says reading from OX7100. So this is an address, think back to our address space that we talked about on Monday. So whenever we try to read from this address, then 1 byte should be accessed using the terminal's std in. So if you are running there's multiple ways to think about the terminal, but in this case, it's probably easiest to just use the terminal that you are running your emulator in. So I guess it depends on how deep you want to go with this, but what I would recommend doing is probably just anytime that you receive, like anytime your CPU receives a read from this address, or read from this address, it should pause and it should basically just run the basic like C++ stdin method. And what would that probably be? Does anyone know how to get stdin using C and C++? What do you do? I think the best way is something called get char. People seen this? Get char, get character. Okay, cool. Okay, getting a couple nods. And then similarly, so anytime now you write to this address, then now this is how you will print out to stdout. So let's double check kind of what's going on. So the hello world program, so if we open up the hello world program, we should imagine that we should probably see some writing to this address. Like we could probably imagine that. So let's open up hello world.slug, and we can open it anyway, open it in our hex editor, and we could scroll down to all of our instructions. And so in theory, somewhere in here, we should probably see that we are going to be writing, we're going to be reading from, is that right? Yeah, we're going to be writing to this stdout value. So stdout is OX7110. So, okay. So do we see that anywhere? Let me see. I actually can't remember. Oh, I'm getting, go away. Thank you. Okay. Actually, I'm not seeing it. Okay, maybe I'm getting confused. Maybe we have to search for it. Oh, actually, I think I see it. Okay, there we go. I just wasn't scrolled down far enough. Okay, so if we can search for. So if I search for 7, I think I need to specify where we search. So I can say search in. Maybe I don't need to specify. Okay, so 710. No, unfortunate. So we just need to look. Okay, anyways, so we can see right here, right? So here we have this instruction. Okay. So this instruction, so it's 90027110. So in your opinion, just by looking at this, in your opinion, what instruction is this probably going to be? Turn to the person next to you. In your opinion, what is this instruction probably going to be? Okay, so if we were to look in the documentation to find out what instruction this is, what's the first thing that we should do? By looking at this number, what is the first value that we should look at to figure out what instruction it is? The opcode. Yeah, okay. How do we find the opcode? Do you remember? So we can go back to the documentation. We can go over to CPU instructions. And okay, so this is the structure right here of how instructions are laid out. So we can see that the opcode is the top how many bits? It's the top 6 bits. Okay, so let's go back to hello world1.slug, and let's check the top 6 bits here. Okay, so what are the top 6 bits, and how do we convert that now to decimal? So if I scroll down a bit, we might actually be able to get the decimal value. Okay, so it's 144, but then divided by 4, I believe, because that would be getting off the bottom 2 bits. It's also, yeah, okay. Anyone know what opcode this is in decimal? 36? Okay, let's quickly double check. So in the CPU instruction, so if I scroll down to the instruction, so we can see, so opcode 0, 18, okay, 36, was that it? So 144, I'm cheating, I'm pulling out a calculator. 144 divided by 4, yeah, 36. Okay, so 36, so this is OR immediate. Okay, so it's loading in this address. Okay, cool. And then after that, then we can, I'm imagining that there's probably going to be a store somewhere in this. So let's quickly find the store byte. Okay, so here's store byte. So store byte should have the opcode of 56 and should probably directly follow this, right? Maybe. So I guess this is maybe another OR-I. Okay. Well, somewhere in this is going to be a store byte. But we can at least see here that we are in some capacity dealing with this std out address. So this std out address, anytime we write to this address, somehow in this, we're probably putting this into a register, and then we are going to be using this address now to write to. And this is how hello world in this program effectively works, is we are loading in this address, and then we are writing out H, and then everything out to this address. And we can even see, so we have H, and then E, and L, and if I keep scrolling down, well, somewhere in here, you can see hello world. Yeah, cool. Okay, hopefully that is making a little bit more sense on how to run the std out commands. Any questions on this? I'm getting not too much engagement. I can't tell if it's because people are lost or if people already know what's going on. Any questions on this? Yeah. Sure. Yeah, so the question was to explain the kind of flow of what everything should look like. Yeah, so that is the next thing that I kind of had planned. Is I wanted to give an explanation of kind of the structure of the entire project. So the first thing that I would like to do, though, so hold on. Okay, no, this is good. Okay, so when creating the emulator, so what are some hardware bits that we need? If you remember from the documentation, what hardware bits do we need? Memory, okay. What else? CPU, okay. What else? GPU, okay. What else? Yeah, sure, I/O. Maybe operating system as well, although maybe that could be lumped in with the CPU or something. Okay, so these are the different kind of aspects that we need. The memory is probably kind of the most important part, though, at least to get started, right? So in theory, we're going to load in all of this ROM data into our memory, and we need to load it in according to the address space. So here is the address space specification. So the idea is, yeah, so the RAM takes up basically the first half, and then the I/O is a little sliver in the middle, and then we have the ROM that follows that. Okay, so that's the memory. And then we will, in theory, have some sort of API to access that memory. So maybe this memory will have some sort of read. We could say read instruction, or we could have maybe read 16 or read 8. And then we can also write. So we could have a write 16 and write 8. And then now we would need some way to make sure that the CPU can actually access all of these methods. Okay, so then we link it together. And so there's a lot of different ways to kind of think about this. Hopefully you've already kind of started thinking about how to organize your files and whatnot. But oftentimes what you'll find is as you start a software project, the first, maybe first time you get code down on the page, it is maybe pretty good, but maybe you uncover a bunch of potential bugs or potential ways where things don't scale anymore. And so what you may need to do is after you implement a really great minimum viable product that you're really proud of, maybe immediately you go and throw it all away. Because now you have all this knowledge of what abstractions now are useful, what helper functions you need. And so now you actually have a good understanding of how to start the project. So the first kind of run is kind of all just as a tester. And then, after that, now you have all this experience. So then you go and implement it all again. Maybe this is now emulator 2.0, where now it's oh, okay, now I know that maybe this function should go in this other class, this function should go in this other class. And so now you've implemented things now for a second time. And finally, now you have the understanding of what is required to implement a large-scale software project. And so now you go and throw all that code all again away, and now start it for a third time. And finally, the third time, now you have all of the experience necessary to actually build a scalable, long-term software solution. This is very common. Another way to do that, to kind of skip the first two steps, is instead to look up sample projects to just see what other solutions other people have made. Because yeah, dealing with all these kind of functions and whatnot can be kind of tricky to even know where to begin starting to organize everything. And so in my opinion, the best thing, what I will always do is I will go on GitHub and I will see has anyone tried to already solve this problem before of how to load in your ROM files and start executing. So okay, I actually posted on Canvas. I posted a couple NES emulators, open source NES emulators. Has anyone looked at these yet? Okay, great. So let me pull them up actually. Just one second. All right, great. Okay, so this is the resources tab on Canvas. Really quickly before we get into the emulator, I just want to mention, so there's, here I listed the Google C++ style guide. I really think that this is one of the best style guides. It's quite popular. It just describes a lot of popular ways of organizing C++ functions. And yeah, when you do Clang format hyphen style Google or whatever, this is what it is referencing. This is the official Google style guide that a lot of other software projects and also a lot of other languages are inspired from. So anyways, Google C++ style guide. Another thing, has anyone watched any of the Cherno's C++ video tutorials? Anyone? Okay, highly recommend these. I think he was like a developer. I don't even remember what game studio, but he is a video game engine developer and has a lot of experience with C++ and has really great explanations on the implementation details that I will be kind of glossing over in this class. And then past that, here is some Git references. So here's the official Git guide, like reference manual. Recommend referring to this on occasion if needed. And then here is a really great YouTube series that explains how to use Git in a modern way. Really like this YouTube series. And then here I have emulators for reference. So I have 2 emulators listed. Has anyone seen these emulators just in general? Anyone played anything on them? Okay, cool. Yeah, so they're both like very established, very old emulators. So you could probably imagine that their code base is probably pretty good, because I know like MESN has been around for almost like 20 years. Like this is an extremely old code base, and if we check it out, then we'll probably see some pretty mature and and well-tested code. So okay, so I just opened it up, so we can see. So we have a lot of files here. The NES is actually quite a bit more complicated than the Banana emulator. We can see all sorts of stuff in here. So we have console, constraints, whatever, header things, NTSC filters, picture processing unit, like all sorts of different files. Okay, so in my opinion, maybe just the first way to get into this is maybe just pulling up the CPU file. So let's start looking at the CPU. So I'll open the header file for the CPU. Okay, let's see if we can kind of get any sort of intuition for how they organize their code. We can see if we can like pull anything out of this. So okay, so if I kind of just scroll through, okay, so we can see that we have something here. You know, honestly, this isn't making too much sense to me, but if I kind of just scroll through a little bit, then you'll see eventually what we'll get is, so I'm about a third of the way down the file, but now we can start seeing that we have all these functions here. These functions, so it says and, or, add, ADC, CMP. Okay, do these look familiar to anyone? Does anyone have any idea what each of these functions are? We got inc, dec, so yeah. Yeah, exactly. So these are just instructions. So this CPU class, this is how they have chosen to create the implementations for each of the instructions. So here, like, this is the add instruction. This is like fully emulated out, like with all the flags and whatnot. We have compare, CMP. This is like, I think the same thing as like a less than or equal to thing. We have inc for increment, so it like counts up a register, it increments it by 1. So this is where all the different functions for each of the different instructions are. And does anyone know what CPU in particular the NES ran on by chance? Off the top of your head? Anyone know? It's a very famous CPU. It's probably like the most, yeah. Yeah, it's the 6502 microprocessor, yeah. Okay, 6502, anyone doing, I don't know, if anyone's like a computer engineering major, that's just something that you should probably just keep in the back of your mind. It's like famous processors of our time. It's like we got the 6502, which controlled like the Apple II, the NES, Commodore 64. We also have the Z80, which powered like the old Pac-Man machines, and like of course like the Pentium processors of the early 2010s and before. So these are, yeah, maybe just kind of important CPUs, just kind of be aware of. Anyways, 6502 is powered the NES. And here are a bunch of 6502 instructions. But we can kind of still use the same sort of idea for our CPU. So instead of 6502 instructions, maybe we could just have a list of all these instructions now for our CPU. But okay, so now we have these instructions, but how do we actually call these instructions? So we have like rotate left, rotate right, but okay, yeah, so where do we actually go from reading in like an instruction, right? An instruction is going to be, in our case, it's going to be a 32-bit integer. It's going to be 4 bytes, and this instruction is going to start with an opcode, and ideally we then go and kind of decode out this integer. We decode it out into whichever function we want to run. So the idea is maybe we take this integer, we check the top 6 bits, and maybe we have like an if statement that's like, if the opcode equals this value, then run rotate left. Or like, oh, if the opcode equals this value, then run compare or something. We could have this big like if chain here. So that's what I'm kind of expecting they're doing. So let me double check that. Okay, we following? Okay. Okay. So if I now go and maybe I'll Google, I'll just search for opcode. I'll see where they are using the opcode, because the opcode is supposed to decode into the function to run. So okay, cool. So here, so get opcode. Cool. So okay, so it's doing a memory read. So similar to what I was thinking. So where we want to read from memory. Okay. So memory read. Good. We can also see. So we got returns opcode, and then here. It doesn't look like there's anything in here because we are in the header file still. So let's go and check the implementation. So maybe in here, in the implementation of the CPU, we can see where the opcode is used. Okay, cool. Oh, great. So in exec. So exec, I guess that's where it executes instructions. So okay, so cool. So we can see that we have this, we're getting the opcode with that get opcode method that we already saw. Good. And then, well, it does something kind of weird. Okay, actually, what the heck does this do? This line right here. Okay, you haven't seen this? Okay, I want you all to turn to the person next to you and explain to them roughly what this function does, and specifically what this line of code does right here. It's pretty cool. Okay. Actually, I'm going to try turning down my volume. I feel like I'm so loud. Oh, okay. Cool. Okay. Good. Okay, wait. So what the heck is going on here? Any guesses? Yeah. It's a jump table. Okay. What could you be more, or could you explain what that is? Oh, okay. So it uses the opcode. So the opcode is just an integer. In this case, it looks like it's an 8-bit integer. And what it will do is it will look at that integer and it will use it as an index into an array. And what will this array give you? Like what does each array cell store? Yeah, it stores a function pointer. It stores like the function itself. So here, like what's happening is we're accessing this opcode table. So we're putting in an opcode, and then we get back a function. And the function that we get back is the corresponding instruction that our CPU needs to run. So yeah, so if we were trying to run the branch instruction, well, all we would need to do is just put in the branch opcode right here, and then it would run the branch instruction. Let's quickly look at this op table, though. So if I search for this now, so okay, cool. So it looks like it does a mem copy where it copies op table into op table. So let's now check this one. Okay, good. Okay, cool. So this is now the op table, so we can see everything that's happening here. And it's a little bit hard because it's, yes, I can hide this. And there we go, cool. So now we can see more of it. It's quite large, but if we zoom in, we can see, so yeah, this is an array. That's what this notation is saying. So it's an array, and so the first instruction, I guess this is a break instruction, and then it's or accumulator, and then HLT means halt. I think it just means kind of like not implemented, and then there's all sorts of instructions, and every single element in this array corresponds with one opcode. So you pass in an opcode, and then it gets you back the function pointer. And so you can see every single function is actually in this table. Yeah. Pretty elegant, pretty cool. And this is slightly better than having a long line of if statements. Because why? Why is this better than if statements? Okay, tell the person next to you, why is this better than if statements? All right, anyone? Maybe someone else? Yeah. Sure, it's constant time. That's the thing I was looking for, yeah. So if statements, if you have maybe 50 if statements, and maybe your opcode is at the very bottom, like maybe you're checking opcode like 64 or something, and you go through every single one of those if statements, it's going to take a long time to go through each one of them, yeah. Versus this, immediately it knows exactly what address to pop over to. Yes, you have something else? Yeah. Absolutely, yeah. So a good point was brought up, about switch statements. Have people heard of switch statements? Okay, cool. So switch statements are another kind of way of implementing like a big if tree that will automatically convert it into a jump table like that. However, this is a little bit more explicit. Not all the time. Switch statements will not always convert into a jump table. Sometimes it will just, like the assembly that is elaborated out, sometimes it will still be a bunch of branching instructions and it'll still be really slow. Versus this is guaranteed to always be constant time. Yeah, cool. Okay, is this changing anyone's code now? It's maybe you already implemented this part in your code, and you're like, shoot, now I got to do it this way because this way is cooler. Anyone doing that? Okay, cool. Maybe I showed you this just in time. Another thing is, notice that in this example, there's actually a bunch of, so if I look at this HLT, I'm pretty sure this means not implemented. Maybe I'm wrong. So there's some instructions that don't do anything here. Similar with the banana slug emulator, there's a lot of unused opcodes. And so maybe instead of having this huge array with every single cell corresponding with one opcode, maybe instead you could use an unordered map or an ordered map where since you don't have every single possible cell needing an opcode, needing an instruction, instead you could just focus on just the individual opcodes that actually exist for your architecture. So it's up to you, but cool. Okay, good. Okay, but now we have the CPU, and so I'm kind of curious though where the CPU is even called. So yeah, because we have the CPU class, and I mean if we go back to all of our CPP files, it's kind of hard to even know where's the CPU being called. I can search for it, and it's here's the CPU, but I don't know where this is being used in this project. Okay, what I would do is I would use the GitHub dev feature. Does anyone know what happens when you click the period button on GitHub? Has anyone seen this? Anyone? Okay, so we got a couple people. Okay, this might blow your minds. Are you ready for this? Okay, so I'm going to hit the period button. Okay. Oh, it's loading something. What's going on? Ooh. Okay. You excited? It takes a second. That's one downside of this. Okay. There we go. Does this look familiar? What is this? It looks like VS Code, but it's running in the browser. See, like it's a browser version of VS Code, and it already has this emulator already like pre-set up. And so now I can go through this as if I had cloned it, and it's great. So now what I can do is I can do like Control-Shift-F, or on macOS it would be Command-Shift-F, and I can actually search for this NES CPU, and I can see every single place in this project where NES CPU is referred to. And maybe I want to just make the search parameters just a little bit more explicit. So maybe I will say only include dot maybe CPP files, or .h. Okay, so cool, so that has shrunk it a lot too. Let's now maybe make it so that it also has to look inside of core, I think it's NES, right? Is that right? We can click on this button right here, which will kind of shrink everything down. Okay, there we go. Oh, I shrunk it too much. Okay, cool. So here we can see the file structure of everything, and every number here, this is corresponding with how many times NES CPU is used. We're probably not going to be using SNES, but we can go to NES, okay? And then here we have all these files. In your opinion, which one of these files most likely is going to have where the instantiation of NES CPU is? So which one of these is probably going to have our CPU? Yeah, probably console, I'm thinking. It's obviously not going to be the CPU. It's probably not going to be the picture processing unit or NES types or whatever this interface is, or any of this stuff. Yeah, so it's probably going to be this console. Okay, so let's open up this console and see where this is created. So okay, cool. So now we have this NES console class, and yeah, we can see that we have a unique pointer to an NES console. Unique pointer meaning that this NES console this NES CPU there's only one of them that exists. Cool, and then we can also see that the console also has the picture processing unit, and also the audio processing unit, and the memory manager. And so we can see that this is how they've chosen to structure their emulator. So they have kind of like you can think of it as like a top class, this NES console, so this top class, which has inside of it, it has the CPU and operating system and everything all in it as members. Cool. Okay. Feeling okay? Okay. Doing this, though, requires some finagling, and I was thinking of walking through how to get this kind of structure set up on C++. Maybe it would be more useful for you to like try to play around with it first, but also I think it would cause a lot of pain. There's a lot of like weird kind of C++ features that you need to do in order to create this sort of structure. But okay, take like 1 minute, maybe think about what sort of difficulties you will run into if you try to create like a top class like this, the NES console, with all of the members like this. Think about it for like a second while I prepare for the next example. We are, let's get into it just a hair. I think maybe we'll return to it on Friday. But yes, okay, cool. So I pre-prepared a fairly kind of similar example. I'll call it a ref, cd into ref. Okay. So inside this, so I have these functions right here, or this main class. So this main class, this main function, it creates a top module and then calls this work function, and then it calls this log function on a logger. Okay, and we can open up this tool class right here. We can also open up the logger, and we can also open up the top class that brings it all together. Getting it all set up. Okay, cool. So yeah, so we can see that top, so it's doing a very similar thing to the console that we just saw, like the console class, where we have maybe, instead of CPU and memory management unit, instead it is just tool and logger. And if we look at tool, so yeah, tool, well, let me zoom out a bit actually, will help. Yeah, so tool, you can see, has this work function, that's all it has, and it just says tool working, and then logger will effectively just call cout. So now if I go and compile this, so if I do C++ main.cpp -o main and /main, we can see that this should just work. Yeah, so we see tool working, and we see log. Okay, but the issue, though, is this tool working should probably, this message right here should probably instead be run inside of our logger class, because maybe our logger class maybe has a method of like disabling like certain messages or maybe sending it to files or things. So we should not be writing this to stdout. Instead, we should be calling our logger class that we declared over in top. So in top, yeah, so we have this logger. So the question now is, from this tool member, how do we like go up like out of this tool member and now access logger? Okay, take a second. Tell the person next to you, brainstorm, what is the best way to do this? Ideally, we should have something like logger.log tool working. All right. There's not much discussion happening. Ask the person next to you what they think a good strategy would be to access the log function from our logger. Okay, any good strategies? What do you think? Yeah. Oh, okay, sure. So maybe we could have a reference to our logger like class over here, our logger class over, yeah, so we can maybe call this logger, something like this, right? Okay, and then maybe we just add like a constructor as well, so tool, and maybe now it needs to take in a logger as reference. And then we can do an initializer list, so we can initialize our logger to be logger. Okay, and then this, where is it? Yeah, and then maybe now our top class, I think we're, oh, my bad. Our top class now needs to also have a constructor. Okay, so we can do top. So logger, oh, sorry, tool needs to have logger passed in. And yeah, and then logger doesn't need anything. Okay, in theory this should be good. Let's see. Okay, cool. Feeling okay? Okay, says I saw a question. We're good. Okay. Okay, cool. So now we have this reference to logger. Okay, and now I think if I run this, okay, so we still get an error, but that's okay. We'll get to that in a second. In my opinion, though, I don't think this is the best strategy. And the reason for that is, remember, so our in this example, sure, it makes sense, but remember that our top class is going to be a console class where we're going to have a bunch of different members that all need to access each other. So if we have like 5 members, that each one of them needs to have 5 references to all the other 5 members, then that would be like 25 references that we all need to continue maintaining. Like we would have like CPU and memory management and everything. Like every single one of our members would have a bunch of links. Okay, so maybe is there a better way, instead of pulling in the logger itself, but instead maybe pulling in something else? Yeah?
Can you just like use the class as like a child class or like have it extend?
Oh, sure, so using inheritance.
Yeah.
I don't think that would work too well in this case. I don't think inheritance would be the best use case. Maybe something else, though. Yeah? Oh, okay, so putting top inside of tool, and then how would you replace this logger reference? I think you're on the right track. Okay. So yeah, I do agree. So it has something to do with putting top here. Okay. What do we need to change here, though? Instead of pulling in the logger member, what instead should we pull in? The top. Yeah, exactly. So that's what I'm thinking. So maybe instead of logger, we can have top. And maybe instead of a reference, we'll just have a pointer. So cool. So now we can have, inside of our tool class, we now have a reference to the top class that also references logger, that also has logger. So now we can do like top arrow logger. And there we go. And I can now replace this with top. Is that good? Okay, cool. There we go. Cool. Okay, so let's see if that is going to work now. I think we'll still get an error. Yes, we're still getting an error. Okay. So I think, though, if I remove this, I think this will still compile. Oh, maybe not. Okay, wait, so let's now fix this. Okay, so what seems to be happening? Oh, okay, so it says top does not have a name. So, okay, so what are we missing from this, from the tool class? We're missing, like, the top header file, right? Yeah, okay. So if we now go and try to include the top header file, okay. Uh-oh. Has anyone seen this before? Anyone know what's going on? Okay, so what just happened is, so it says no previous definition of class top. But like, what does that mean? Like, previous definition of class top? Like, I'm only declaring top in one place. Like, I'm only declaring it here. But for some reason, it thinks that I'm, like, declaring it multiple times. Well, that's because if we look at the order of how things are included, so first we include top.h, okay? Then that means that we effectively just take this file and we copy it in. What include is you just take a file and you just copy it in place. So what happens is we go like this. Okay, boom. Now, what's next is, well, now we include tool.h. Okay, so now we take tool.h, which is this file, and replace this out. Oops. Okay, well, now this includes top.h. Okay, so now we can take top.h. Okay, well, now this takes tool.h. So now we take tool.h. So they are referencing each other infinitely. And so if you saw, it was taking like forever to compile this file because it was like doing this forever loop where it was including one file, including one file. Okay, how do we fix this? Yeah? Pragma once, yeah. So there is a strategy that what people will do is something called header guards, or in modern C++, it has been kind of replaced with something called pragma once. So what you should always kind of do is anytime you have a class, anytime you have a header function, is you should make sure that that header function is actually only ever included just one single time. So what we can do is take, so that this top class, we don't want it to be included several times. And if it ever is included like at another time, then we want to add a guard around that to prevent it from being included again. First, let me just undo like all this stuff that I did. Okay, so I think that was the main thing. Yeah, cool. So what the most popular thing is we can do a define for the file. So we can define this as often we'll see like a double underscore, and we'll say like top underscore h. This is kind of arbitrary, but usually we'll see like anytime you include this file, now we will have this macro that is defined. And a macro is just something that the compiler sees. And so if we wanted, we could define this to have a value. We could say like 1. Now, anytime that this macro is ever seen somewhere else, then now it will elaborate out to this value. We can also just leave it off, and we could say like, oh, define this just like empty macro, just so that it exists in the compiler. And then what we can do is we can check like, okay, well, does this already exist? So the way we do that is with if define, if def, and we can check. So if top.h, sorry, if I guess, yeah, that's fine. We can check if this already exists. Okay, and if top.h already exists, then we should, like, maybe let's say like down here, right? So if top.h already exists, then that means that we have successfully included all of this code. So we're good. So if we ever have this moment here where we like include the file twice, what we'll see is we will have this bit of code down here will start to be run. But I'm getting ahead of myself. Okay, so instead what we could do, though, which would probably be a little bit more helpful, is just every single time that we enter this file, we can just check. It's like, well, first, like, does this exist at all? We can say, like, if it's not defined, then we can create it. And we can also, oops, and if. So if this file like does not exist yet, then please define it and include all of the code for it, and then go and exit this if statement. So this is how header guards work, is we say like we're defining this file at the same time that we're also defining all of the code that goes inside of the file. Cool. Anyone seen this structure before? Header guards? Okay, fantastic, great. We could also, if we wanted, we could replace all of this with something more modern, where it's just, you just type in hash pragma once. Okay, has anyone seen this before? Pragma once? Okay, cool. Pragma once is the exact same thing as this, these header guards. Cool. Okay, so let's go and throw pragma once now on each one of these, and so that will at least now fix the infinite loop. So okay, let's now rerun this. Hopefully this now works. Okay. Unfortunate. So things are still kind of failing. Okay. It says top does not have a type now. Okay. So we still have the same problem. Okay. Now the problem is though. So we include top, then So we take this top, right, include this in. Okay, and this top is now properly included. But then we have this tool.h. So then this tool.h goes in first. Okay, well then we include top.h. But top.h has already been declared. So the issue now is there's not actually any way to know like what, the issue is we actually cannot have this like self-referential thing right here. We cannot have a top like class reference the tool class, and then the tool class reference the top class. You can't have this in header files. So instead, what we do is we make a .cpp file, because in .cpp files, you can, in fact, have this referential thing. So that is the purpose of CPP files. So, okay, let's go and create a CPP file for tool.h. Okay, good. So our tool, what we can do is just, we get rid of this include top, but in our .cpp, we can include the top. We can also include tool. Okay, and now we should, pull out this work function. Okay, there's that. Good. We can now change this to now be constant. Okay, we're still getting an error on top though, but remember we can't include top. So what we can do instead is maybe something that you've never seen before. We can just include a declaration like this. This is called like a stub class. I'm sorry, that's not what I'm looking for. It is this, where you create a stub class, where you just create a class and then give it a name, and you're basically just saying like, hey, this eventually will exist. Like, don't worry about it for now, but like eventually, like you'll be able to find it later. In that, as long as you're dealing with pointers like this, C++ is perfectly happy just assuming that eventually this top class will exist. So okay, let's go in and test this. Okay, so if I now compile, but I need to also include now this CPP, this tool.cpp. Slow. Okay, tool.cpp. Okay, good. So I think we've gotten some different errors now. So this is great. Oh, so we accidentally included pragma once inside of our main. Oh, it's because we just need to get rid of all that weird example stuff. Okay, so now our main is kind of back to normal. Let me zoom out a bit. Full screen. Okay, cool. Okay, let's check this now. Okay, good. Slightly different error. Okay. So tool.h, of course, we no longer need this. So we're not passing in logger anymore. What is now the argument to our constructor for tool? Yeah, it's going to be top. So how do we access now top? So top is like this object. So how do we pass top into tool? This. Yeah, great. Okay, so let's try again. Okay. Good. Okay, we still have pragma once in top file. That is a little weird. Okay, but at least, okay. Actually, why is that happening? That's very odd. Oh, because I have it in a CPP file. My bad. Okay, good. Okay, so in theory, so now this should be working. Okay, cool. So now we have tool working and log. Okay, so it's kind of a lot of just detail stuff that you need to do in order to get this structure working. But this is kind of just what you need to do for getting started with your banana sled project. So yeah, this lecture will be recorded, so I highly recommend, like, as you're going through this, if you're having trouble, like, with your kind of self-referential stuff, to go back and check. Let me quickly, I might still have a bug because I'm not actually calling logger, so let me quickly check this. There might be still one more thing. Are we good? No, we're good. Okay, yeah, so you can see now we are calling logger from work. Instead, if we wanted, instead of this tool, maybe you could imagine this is CPU, and now we are calling CPU, we're calling our, like, memory functions from our CPU class. Yeah, question?
Do you post these files anywhere from, like, after the lecture other than recording?
I post all my lecture files on Canvas.
Oh.
Yeah. I didn't post last lecture's files yet, but I will. Yeah. Yeah, any other questions on this? Okay. Feeling okay? Okay, you're all experts. Thank you. I think that is a good place to end for today. So we will meet again on Friday, and we will talk even more about the final project. And hopefully, maybe at least a couple teams are going to be done with homework or with Hello World 1 by then. So, okay, cool. Looking forward to it.